All right. Close this out. Check Zoom one more time. Okay. All right. So, welcome, gentlemen. Hopefully, you all enjoyed your homecoming. Yeah. I don't know. More else, like we don't ever win. Like I don't remember the last time we won a homecoming game. I don't know what that's about, but you know, it is what it is. Hopefully, you were able to enjoy yourself on some level. The only real major announcement this week is, you know, we have exam 3 that should become available. It should become available this upcoming Sunday at 11 a.m. It'll be due the following Sunday, and it's going to cover chapter 2, right? So with chapter 2, we've been kind of going over sequences and series. I think last week we worked on arithmetic sequences where we were adding the same thing each time. So there's another one that we're going to talk about today. So, you know, we have our usual setup or structure of the class. It is remote asynchronous, so you know the spiel there. If you have questions, feel free to either unmute yourself to get my attention. That's the best way to get my attention, or you can type your questions in the chat. I do check the chat periodically, and I will check Zoom again around the 15-minute mark for anybody that missed the first wave of attendance. So let's kind of look at this. So this is going to be the last of the new material for exam 3. This stuff is going to be over in the blink of an eye, right? So we have this section. We have this week, which is this section. Next week is going to be all exam 3. So next week, you know, for class, I'm just going to be on the call, just taking attendance and just answering questions. Otherwise, I'll just be on the call in silence next week. So you just check in. If you don't have any questions, you can get your attendance. You know, you don't have to stay. But you can ask questions about anything that's on Pearson, even the current exam you're working on. If you work on the exam at that time, you can ask me and we can work on it together. Like, it's not a big deal. You know, because you know how it goes. If you get it wrong, or if you don't like the score, you could do it again, but it's going to give you a completely different exam, right? So hopefully you guys have devised some kind of plan that's working for you. But with that, let's go ahead and get into section 2.3, dividing polynomials and the rational zero test. Oh, sorry. I totally said sequences and series. Sorry, that was my other class. You guys have been doing chapter 2. I don't know. I can't even think of what the concept was. It's things centered around polynomials. Sorry, sequences and series were my College Algebra 2 course, not you guys. So with section 2.3, we have dividing polynomials and the rational zero test. So a few objectives here. We like to learn the division algorithm, use the remainder and factor theorems, and use the rational zero test, right? Okay. So first we want to introduce this concept of what we mean by a polynomial factor. A polynomial d of x is a factor of a polynomial f of x if there's a polynomial q of x such that f is going to be d times q, right? So the f we call the dividend, d we call the divisor, and q we call the quotient, okay? So here. So if a polynomial f is divided by a polynomial d, where the divisor is not 0, there are unique polynomials q and r such that f divided by d is going to be q plus r over d. If you use algebra to solve for f on the left, multiply both sides by d, you get the dividend is equal to the divisor times the quotient plus the remainder, right? So that's kind of a mouthful. The simple explanation here is that the division algorithm is going to parallel the same way we do regular long division, right? Let me see. Hopefully it allows me to add a page. It's kind of been throwing a tantrum all day. Yeah, still kind of throwing a tantrum. Give me just a moment, guys. So I have to like close this out. I can close that. I think I have to like. Let's go back. Let's close it out again. Let me just pop this off. I'll fix everything in just a moment. It's just, I don't know, it's been throwing a tantrum. Like every time I try to add a page, it kind of acts like this. I might need to do an update or something. Let's see, I left off. Oh, this isn't even the right class. This one. Okay. I'm gonna add a page. And then I want it to be like this and apply. Okay. Let me hop back over here. Let me see. Okay, let's share the screen. Okay. All right, sorry about that. Okay, let's give it a go again. All right, so we left off, we talked about this. So for instance, to kind of put in context what we're going to be working on today. That's fine. So for instance, the time now is 3:07, right? Let's see, 10. Okay, let's put a 2 here. And let's do 6, all right? So if we were dividing, if we were just doing regular long division, you know, first we would say what? How many 6s are in 30? 6 times 5, right? So that would be 5. You would get 30. You get your 0, and a 7 comes down. How many 6s are in 7 is 1. And then you multiply, subtract, and then the 12 comes down, right? How many 6s are in 12, which is 2? 12, and we get a remainder of 0. So the same way we did long division here, we can do this concept or this technique called polynomial long division. So we're asked to use long division and synthetic division to find the quotient and remainder when this dividend is divided by this divisor, okay? I'm gonna have to try this again. I need 2 pages. There's one, it's looking good. And the second one, okay. And then I want to get a copy of this. Click it here. And I just want this guy. Okay, we're gonna take that and drop it right here. Oh, come on. Okay. And then let's go like this. Come on. Come on. Okay. So first, we're going to do a demo on polynomial long division, right? So first thing is our divisor goes over here. So we got this x plus 2. And we're dividing into this dividend, which is 2x to the 4 plus x cubed minus 16x squared. Now, every power has to be accounted for. Notice we have a power of 4, power of 3, power of 2. Power of 1 is missing, so we need a placeholder. And then the constant term. Okay? So this is how we set this up. So then when we go to do our division, it's similar to how we did long division. We're going to say this first term divided by this first term. So 2x to the 4 divided by x is going to be 2x cubed. Okay. And then on a diagonal, we multiply. So whenever, in this case, whenever we're going to diagonal, we're multiplying. Okay. So then 2x cubed times x is going to be 2x to the 4. Okay. 2x cubed times 2 is going to give us 4x cubed. Okay. And then now we're subtracting, so we need to distribute a negative. Okay. A number plus its opposite adds to 0. 1 minus 4 is negative 3x cubed. And then this 16x squared just comes down. Okay. So then negative 3x cubed divided by x is going to be negative 3x squared. Diagonal, we multiply. So this negative 3x squared times x is negative 3x cubed. Negative 3x squared times 2 is negative 6x squared. And then since we're subtracting, we need to distribute negative. A number plus its opposite adds to 0. Negative 16 plus 6 is negative 10x squared, okay? Then the 0 comes down. So you'll notice that the steps parallel, like what we did a moment ago. It's just, we're using polynomials instead of numbers, or in conjunction with numbers. Okay. So then this 0x comes down. We say the first term divided by the second, negative 10x squared divided by x is going to be negative 10x, right here. Okay, then we multiply negative 10x times x, negative 10x squared. Negative 10x times 2 is negative 20x. Distribute the negative, so this becomes positive, this becomes positive. And this is supposed to be squared. A number plus its opposite adds to 0. Here we have 20x, okay? I think the 18 comes down. Okay. And then we're almost there. 20x divided by x is going to be 20. Notice with my quotient, I'm lining up my like terms. Lining up my like terms. Right, okay. On the diagonal, we multiply. 20 times x gives us 20x. 20 times 2 gives us 40. We subtract. This adds to 0. And I think that's negative 22. Go away. Negative 22. This is our remainder. Okay. So we got this quotient with that remainder. So that was a demo on, hang on, let's see. Of course, this is what I want to do. It's not going to just let me move that. How do I unattach those? Okay. It didn't used to do that. Okay, I don't know how to get rid of that. Okay, I'm not gonna worry about it right now. Sorry. Oof. All right, so we'll just go with it for now. But yeah, we got that result. So now, let me see. I can at least copy. So that was a demo on polynomial long division. Oh. So I thought I added another page. Oh, okay. I see what's going on. So now let's do a demo on synthetic division. And let's paste. Nope. Copy. Paste. I guess I just have to erase it. Okay. What's the time? Okay, I'll check Zoom in just a moment. Okay, so we saw a demo on polynomial long division. So now let's do a demo on synthetic division. Now, when we do synthetic division, the first thing is we have to identify the zero of the divisor, right? So here, our zero is going to be -2. So that means that we put -2 into the chair. Okay. Then we take the coefficients. So it's going to be 2, 1, -16. Now notice that the power of 1 is missing, so we need a placeholder just like before, and then 18. We started with the degree 4 polynomial, so that means we should have 5 numbers. 1, 2, 3, 4, 5. Okay. So when we do synthetic division, the first number just comes down. So that's going to be 2. And then on the diagonal, we multiply. So on the diagonal, we multiply. Vertically, we add. Okay. So -2 times 2 is going to be -4, plus 1 is -3, times -2 is 6, plus -16 is -10. We multiply. So we positive 20, 20, -40, -22. So the -22 is our remainder. Okay. So because we started with a degree 4 polynomial, that means at this stage we now have a degree 3. And then squared, and then x like this, all right? So this is what we call the depressed equation, this guy here, all of this, okay? But it's the same result that we got here on the previous slide. Okay, so we saw 2 different ways. Now, the thing about synthetic division, although it's easier, we can only do it when we're dividing by a linear binomial. So when we're dividing by something that takes on this form, where it looks like this. Okay, sometimes if we're not dividing by a linear binomial, then we need to use polynomial long division. Okay, here's a type version of what we just did. Okay, let me take a moment to check on you guys in Zoom. Let's see. Okay. Ooh. Oh. Okay. Let's keep going. Okay. So if a polynomial f is divided by x minus a, then the remainder is given by this, right? So if we're dividing by x minus a, then the remainder is going to be f evaluated at that a, right? That's the remainder there. Okay, so find the remainder when this polynomial is divided by x minus 1. So the remainder theorem says that the remainder is going to be the same as f of, in this case, our a is 1. So then if we just evaluate this when x is 1, that'll give us our remainder. So 2 times 1 to the 5th power minus 4 times 1 to the 3rd power plus 5 times 1 squared minus 7 times 1 plus 2, okay? That's 2 minus 4 plus 5 minus 7 plus 2. So then if we combine like terms, 2 plus 2 is 4 minus 4 adds to 0. 5 minus 7 is -2. Okay. So then this is our remainder. And we can confirm that this is the case if we do synthetic division. If we do synthetic division, the remainder should be 2. Sorry, -2. Okay. Let's do synthetic division quickly here. So if we're going to do synthetic division, if we're dividing by x minus 1, our 0 in that case is 1. So that's what goes in the chair. The coefficients are 2. Now the 4 is missing, so that means we need a placeholder. 5, 4, 3. So then we get this -4, 5, -7, and 2. Right? We started with a degree 5 polynomial, so we should have six coefficients. 1, 2, 3, 4, 5, 6. Okay. So then if we do synthetic division, first the 2 comes down. Diagonal, we multiply, we add, we multiply, we add, we multiply, we add, we multiply, we add, oops, we multiply, and notice that our remainder is indeed still -2. Ouch. So we saw two different ways in either case. When we evaluated this function when x was 1, we got -2. When we did synthetic division, the remainder was -2. So we showed that they're the same. Okay. So then let f be this, find f of 3. All right. So we can also use the remainder theorem in reverse. Instead of just plugging in when x is 3, we can do synthetic division, and then the remainder will be f of 3. Okay. So in this case, we put the -3 in the chair. We write our coefficients in the form of 1, 3, -5, 8, ouch, 75. Okay. The 1 comes down, we get this. -3 times 1 is -3. We get 0, 0. We add vertically, diagonal, we multiply to give us 15. If we add, we get what, 23. If we multiply, -69. And then we get a +6 is our remainder, right? So if we want to find f of -3, that's going to be the same as our remainder, which is going to be 6 in this case. Okay. You see it both ways here. Here they evaluated, they plugged in -3, they got an answer of 6. When they did synthetic division, they got a result of 6. In either case, they got 6. Let me check on you guys real quickly. Okay. So a polynomial f of x has x minus a as a factor if and only if f of a equals 0, right? So if we're dividing a polynomial by some linear binomial, we say that this guy is a factor of f if the remainder is 0, right? That's basically what the remainder theorem is saying. So given that 2 is a 0 of this guy, solve this polynomial equation. So we've been given 1, 0, so it's a good idea to confirm that it is indeed a 0, right? So if 2 is our 0 and we do synthetic division, the remainder should be 0. Okay, we got 3, 2, thank you. Let me see, 3, 2, 1, 0. So we don't need any placeholders. 3, 2, -19, and 6, okay. The 3 comes down, on the diagonal we multiply, we get 6. We add, we get this, 16. What is that, -3, -6. Notice that the remainder is indeed 0, okay. So we confirmed that 2 was indeed a 0. So now at this point, since we started with a degree 3, this is now a degree 2 polynomial, okay? So at this point, we have, if we list out our factors, since 2 is a 0, that means that x minus 2 is our factor. And we want to try to factor this 3x squared plus 8x minus 3. The whole point is we're setting this thing equal to 0. Okay. So let's see. So we're looking for two numbers that multiply to give us -9 and add to give us 8. And that's going to be -1 and 9. But I'm going to use the box method for factoring to complete this factorization. Okay. And the focus is going to come on this guy in orange. It's going to come from this. Okay. So now in the upper left-hand corner goes the 3x squared. Bottom right-hand corner goes to -3, okay? And we're gonna rewrite this orange 8 using the two numbers that we found, okay? So 8x can be rewritten as 9x plus -x to give us 8x, okay? So now to finish out the box method, if we look at the two numbers on top, what's the GCF or what do they have in common? What can we factor out of the two on top? We can factor out 3x. Okay. If we look at the two on the bottom, what can we factor out? It's -1. Okay. The two on the left, what do they have in common? They both have x. And what can we factor out of the two on the right is a +3. Okay. So then our claim is that the polynomial on the left is going to factor into the following. Now this x minus 2 just comes down. And our claim is that it factors into 3x minus 1 times x plus 3. So that's a demo on the box method of factoring. Okay. So then now we have three things that multiply to give us 0, so we can use the zero factor property. When two or more things multiply to give us 0, we just set each thing to 0 and solve. And if we do that, we'll get x equals 2, which was the one that was given. We'll get a third, and we get -3. Okay. So these are zeros. If this were a testing environment, it would be a good idea to plug these into the original to make sure they all work. Sometimes this produces what's called the right-wrong answer. I call it the right-wrong answer. In that algebraically, everything is sound, but then sometimes we'll produce things outside of our domain. So that's why it's always a good idea to check whenever possible. Okay. So we got 2, 1/3, and -3. I'm just going to piggyback off of my prepared notes for right now. And I think they kind of did the same thing here. 2, 1/3, and -3. Okay. All right. I think I might just leave this one as an example or as an exercise. If you want me to, like, I have it in my pre-recorded notes, I just don't feel like doing it right now. If you want to see it, just say it and we can do it right now. Otherwise, I'm gonna leave it as an exercise. Okay, it's totally doable. And I think I'm gonna refer to my prepared notes, my prepared lecture on this one as well. But let me just touch on this since we have a good amount of time. Let me just kind of touch on this really quickly. So we have the rational zero test, right? So given some polynomial function, right? So it's just a polynomial function with integer coefficients. So all of these ANs, these are just integers, where the leading coefficient and the constant term is not 0. And P over Q is a rational number in lowest terms. That is a 0 of f of x. So then P is going to be a factor of the constant term, and Q is going to be a factor of the leading coefficient, okay? So the rational zero test here, give me a moment. So when we go to do the rational zero test, what we want to do is list out all the factors of the constant term, list out all the factors of the leading coefficient, and then we want to, let me see. It should be. So basically what we're saying is that when we look at all the combinations of the factors of the constant with the factors of the leading coefficient, when we look at all those combinations, if our polynomial has a rational zero, it's going to be somewhere in that list, right? This list that we generate are not the actual zeros, but again, if this polynomial has a rational zero, it's going to be somewhere in this list. Let's take a moment to give it a go. So here we're asked to find all the rational zeros of this polynomial, right? So if we do the rational zero test, our P over Q, okay? looks like they're using this color. Let's do P over, yeah, I think that's that color. P over Q. Okay. So the factors of our constant term, it's just going to be plus or minus 1 and plus or minus 3. So it's just 1 and 3 in that case. Divided by the factors of our leading coefficient are just 1 and 2. So plus or minus 1 and plus or minus 2. So then we want to do all the combinations of everything on top with everything on bottom. Okay. So let me see. We can have plus or minus 1, plus or minus 3. Because if you do 1 over 1 is 1, 3 over 1 is 1. And then you could also do plus or minus 1/2 and plus or minus 3/2. Okay. So again, if this polynomial has a rational zero, it's going to be somewhere in this list. Okay. So I'm going to start with 1, and I want to test if 1 is a 0, that means our remainder will be 0, right? So I'm just gonna invoke the remainder theorem. So if the remainder is 0, that means it's a factor. So I want to find the remainder. So what I'm going to do is evaluate f of 1. I'm just going to evaluate if we plug in 1, all right? Okay. So I want to see if 1 is a 0 of this guy. So if I plug in 1, we're going to have 2 plus 5 minus 4 minus 3. Let me see. 7 minus 7, it looks like it's a 0, all right? So it looks like 1 is a 0, okay? So if 1 is a 0, let me just go ahead and do synthetic division really quick. So if we put 1 in the chair, let me see, we got a power of 3, 2, 1, and 0. So we don't need any placeholders. We can just take the coefficients. We'll have 2, 5, negative 4, and negative 3. If we do synthetic division really quickly, 2 comes down, 2, 7, 7. What is that? 3, 3, and then 0. Okay. So because we started with the degree 3, at this stage, we're now at a degree 2. Okay. So let's keep working here. So if 1, let me see, find all the zeros. So we found 1. So now we just want to factor this guy. Are there 2 numbers that multiply to give us 6 and add to give us 7? And I think it's 1. It's 1 and 6, right? Okay. I'm gonna just use the box method for factoring again quickly. Upper left-hand corner goes the leading term, which is 2x squared. Again, what we're doing, we're rewriting this 7x. This is a factoring technique. Rewriting the 7x using the 6 and the 1 that we just found. The bottom right is our constant, which is 3. So we're going to rewrite 7x using the plus 6x and the plus 1x. Okay, it came from here. Okay. So then, if we look at these 2 numbers on top, what do they have in common? What can we factor out of these 2? It's going to be what? 2x. What can we factor out? What can we factor out of these 2 guys here? I think the only thing they have in common is 1. These 2 on the left, what can we factor out? They both have x. And these 2 on the right, what can we factor out? They both have a plus 3. Okay. I'm running out of space here a little bit. So then it looks like this 2x squared plus 7x plus 3 factors into x plus 3 times 2x plus 1. Okay, I'm kind of out of space. So we found 1 0. So here, it looks like all the zeros that we get, it looks like our zeros are, 1 was the first one that we found. Then from here, we get what, -3 and a -1/2. And again, we need to confirm that these work, that these, when we plug these into the original, that we indeed do get 0. Okay. So what I'm going to do is break out my trusty dusty rusty. The time, this will be it because it's pretty much out of time. I'm glad we were able to do this one though. Okay. That's fine. Okay. Equals, okay. We got 2x to the power of 3 plus 5x squared minus 4x minus 3, okay. I'm going to call on this function that I just typed in. So when we put 1 in, the output should be 0. When we put in -3, the output should be 0. And when we put in a -1/2, the output should be 0. Okay. So we just confirmed that those 3 results are indeed zeros of the original polynomial. And that's about all that we can do there. So again, P comes from the factors of the constant term. Q comes from the factors of the leading coefficient. You see the list on there, we generated the same list. So begin by testing with 1. If it's not a rational 0, then try another possible 0. Okay, I think we did all of that. And we got the same result. Okay. So we only skipped 1. That wasn't too bad. Are there any questions? Do you have any questions? So let me send this to Box. Okay. So when this bar finishes loading, you'll get a copy of what we were working on. And if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, see you next time. Take care. Peace.